And finally, peer into the expanding future.
Okay, let's dive right into this, because before we talk real cosmology, we kind of need to clear up a massive cultural overlap. Look, if you search for the Big Bang Theory, you're probably going to find Leonard, Sheldon, Penny, and the rest of that geeky Pasadena crew. And hey, while that hit sitcom ran for 12 seasons, today we are focusing strictly on the foundational physical model, the science, describing how our actual universe expanded from an initial state of crazy high density and temperature.
Which brings us to a really fundamental question. Before we can track the evolution of stars and galaxies and all that, we have to understand the mechanics of the event itself. So, what actually is the Big Bang? Well, it is incredibly common to picture it as this giant fiery explosion of matter just violently throwing debris into a pre-existing empty room. But actually, scratch that. That's a total myth. The fact is, the Big Bang describes the intrinsic expansion of space itself. There was literally no surrounding space for it to explode into. And the crazy part? The name itself is kind of just a historical joke. Back in the mid-20th century, physicist Fred Hoyle, who actually hated this theory, coined the phrase Big Bang on a radio show just to give listeners a striking image. He was trying to highlight how ridiculous it sounded compared to his own steady-state model. But, ironically, the catchy name stuck like glue. Even though bang implies an explosion and sound, neither of which really described the rapid stretching of the fabric of space.
All right, with that fundamental mechanic under our belts, let's move right into Section 1, the cosmic timeline. We're going to track the expansion and chart the chronological sequence of the cosmos. To anchor our scale here, consider this exact number. Thanks to incredibly modern measurements and satellite data, cosmologists aren't just guessing the age of the universe anymore. They place the initial singularity at a staggeringly precise 13.787 billion years ago, give or take exactly 0.02 billion years. Just think about that precision for a second.
So, how exactly did we get from a tiny singularity to, well, today? Here are the critical milestones we're going to explore. We hit play at 0 with the Big Bang, hit a primordial soup phase at just 1 single second, forge the first elements at 3 minutes, clear the cosmic fog at 380,000 years, and finally arrive at the incredibly complex universe we're hanging out in 13.8 billion years later. And this brilliantly illustrates our whole journey. It acts as a sort of visual home base for us. Notice the overall shape. It's not a static box, right? It's like a giant funnel. Time is moving forward, and that vertical expansion represents the actual size of the universe. In the beginning, you get that initial burst of light, followed by just ridiculously rapid expansion, the formation of the very first stars, and then this massive, beautiful web of galaxies developing as the funnel just keeps growing outward.
Let's zoom in on the very beginning of that timeline, right after the singularity. Around 13.8 billion years ago, for just a microscopic fraction of a second, the universe underwent what we call cosmic inflation. And guys, during this tiny window, space expanded faster than the speed of light by a mind-boggling factor of 10 to the 26th power. I mean, no way, right? Scientists believe this hyper-fast stretching is exactly why the universe appears so mathematically flat and uniform on a large scale today. It essentially ironed out all the cosmic wrinkles in one go.
Now, having all that space is great, but we need matter. That brings us to Section 2, forging the elements, building matter. Where did the fundamental building blocks of you, me, and literally everything around us actually come from? To answer that, we have to look to a process called Big Bang nucleosynthesis. At about 1 second after the Big Bang, the universe was this impossibly hot primordial soup, sitting at roughly 18 billion degrees Fahrenheit. Obviously way too energetic for any complex structures to survive. But as space expanded, it started to cool down. Right around the 3-minute mark, the temperature finally dropped just enough for protons and neutrons to slam together and actually stick. In this tiny, crucial cosmic window, the universe forged its very first atomic nuclei. We're talking primarily hydrogen, a good chunk of helium, and just tiny trace amounts of lithium and beryllium.
But wait, things were actually still too hot for complete proper atoms. For thousands of years, this vast sea of free-roaming electrons created a literal cosmic fog that scattered light everywhere. The universe was completely opaque. You couldn't see a thing. It wasn't until 380,000 years after the Big Bang that a massive event called recombination kicked in. The universe cooled down sufficiently for all those loose electrons to finally bond with the nuclei we were just talking about, forming neutral hydrogen atoms. This is an absolutely huge milestone because it finally lifted the fog. The universe became transparent, and light could actually travel freely for the very first time.
So how do we actually know this whole timeline is accurate and not just guesswork? Let's get into Section 3, Pillars of Evidence Proving the Model. It is time to look at the hard, observable science.
So the crucial point here is that Big Bang cosmology doesn't just rest on one lucky observation. It rests on what scientists call the 4 pillars. These are Hubble's law, which proved that galaxies are moving away from us at a speed proportional to their distance, the cosmic microwave background radiation, the mathematically precise abundance of primordial elements we just mentioned, and the evolution and distribution of large-scale galaxies. Together, these 4 pillars effectively crushed the competing steady-state theory and firmly cemented the Big Bang as our working scientific model.
And it is amazing to see how our evidence gathering has leveled up over the years. Remember that light release during recombination 380,000 years in? Well, that light is actually still traveling through the universe right now, vastly stretched out as microwaves. Back in the 1960s, scientists using a massive horn antenna accidentally detected this faint, uniform background noise coming from literally everywhere in the sky. That was the cosmic microwave background, the literal, physical afterglow of the Big Bang itself. And then jump to today with modern equipment like the WMAP satellite. Over the decades, we've gone from hearing a fuzzy radio signal to launching highly sensitive tech into space to map out this ancient radiation with just stunning high-resolution precision.
And it's not just about the leftover light either, it's the intense math behind the matter. Theoretical calculations of exactly how much hydrogen and helium should have been produced span a staggering 9 orders of magnitude. And here's the wild part. When astronomers look out into the universe today and measure the composition of pristine gas clouds, the observable elements match those original theoretical calculations perfectly. For sure, that level of agreement is undeniable mathematical proof supporting the Big Bang model.
All right, let's guide our analysis to our final stop today, Section 4, the expanding future, looking at the ultimate fate of our universe. Where exactly is all this ongoing cosmic expansion actually taking us?
Let's see how this builds back into our main timeline. If we look at the later stages of our cosmic model, you'll notice that the outer boundary, the shape of our cosmic funnel, doesn't just keep going in a straight, predictable cone. It noticeably flares outward at the very end. See, for billions of years, the gravitational pull of all the matter in the universe was actually putting the brakes on, slowing the expansion down. But then, the shape just flares. And that flare represents a massive, surprising discovery made in the late 1990s using distant supernovae. Scientists realized that about 8 to 9 billion years after the Big Bang, the expansion of the universe completely stopped slowing down and actually hit the gas. It began to accelerate. They attribute this to something called dark energy. It's this deeply mysterious property that essentially repels matter. And here's the truly bizarre part. Unlike normal matter or even radiation, dark energy does not dilute as space expands. As the universe gets bigger, dark energy just becomes a more and more dominant accelerating force.
Which leaves us staring right at the far edge of that expanding funnel, with dark energy pushing the very fabric of space apart faster and faster with every passing second. What is the ultimate fate of our universe? Will it just expand forever until the last stars burn out in a freezing heat death? Or could it literally tear itself apart in a big rip? Well, that's something to chew on. Thank you so much for joining me today to decode the scientific explanation of the Big Bang. I really hope this explainer has left you deeply curious about the enduring mysteries of dark energy and the incredibly vast, expanding future of our cosmos.